morning, everyone. Thanks for coming. We're going to talk today, as you can see from the title, about function templates in C++. We'll see how they really work. In particular, we're going to describe compiler actions, not in algorithmic detail, but to make sure that everyone has a sense of how function templates are processed. We'll talk about synthesis and instantiation. We'll talk about template argument deduction. We'll encounter other algorithms such as name lookup, overload resolution, partial ordering, and so on and so forth. We'll talk a little bit about function template specialization, why we shouldn't take advantage of explicit specializations and what we should do instead. And as time permits toward the end, we'll talk about some things that are in the pipeline for C++20 that are on the topic of function templates. And with that, let's start with some background information. When I was first preparing this talk, I went online to see what people were saying about function templates and discovered that there appears to be a tremendous amount of misinformation, which I like to call, as you see, myth information. So I'd like to quote a couple of these websites. I will not, as I usually do, I will not, however, this time tell you where these are from because I don't want to embarrass anyone, but I do want to counter some of these myths very quickly. There's a website that claims that function templates are special functions, and that is simply not so. Function templates aren't functions, C++ functions of any kind. They're not functions. Therefore, they can't be special functions. Recall that in C++, the term special functions has a very precise meaning. It refers to that collection of constructors and destructors and assignment operators that a compiler can sometimes generate for us. But no special function ever arises due to a function template. Ever, ever, ever. You may be writing a template that looks like a copy constructor. It isn't. Never. Never, never, never. Can't happen. And speaking of special functions, C++ kind of co-opted that term. That term actually has a 200-year-old history in mathematics. Special functions at the high school level refers to, for example, the trig functions, exponential, things like that. At the university level, it refers to things like Bessel functions, Neumann functions, Laguerre, Legendre, and so on and so forth. And just a small sales pitch, I had a bit to do with this. Since C++17, we now have a whole lot of extra special functions in the CMath header. Not in math.h, because we don't own that, but we do own CMath. So if you do heavy-duty mathematics, do please have a look at what's new in the CMath header since C++17. The C++ committee has been working on that for 15 years. It took me 15 years to get that into the standard, but it's now there. So, second quote. Somebody claims that a function template behaves like a function, and that's not so. There's absolutely no function-like behavior that attaches to a function template. For example, you can't call a function template. It may look like it, but you're not doing that. You can't call a template. You can't take its address. It doesn't even exist by the time your program is compiled. So how can you possibly call it, for example? It's not there, right? Final comment, somebody is introducing an example and says, here is the templated function. Well, there's no such thing. We have function templates. We do not have template functions. The C++ 98 standard used the term template functions, and 20 years ago we erased all of that. We have function templates. It's important to use the words in the correct order. My favorite example of this is chocolate milk versus milk chocolate. The one's a beverage, the other one's a candy for children. The order of the words does make a difference, okay? So function templates is the correct term. So if you're either rusty or a little bit new to C++, a very quick introduction. What's a function template? Let's look at it by example. Here's a very simple little function that returns the minimum value of two values. Given two ints, it was going to return an int. Now, you might want to quibble a little bit about the algorithm, but that's a topic for a different talk. But nonetheless, that function, if I just changed int to say double, it would work just fine. for doubles. If I change double to stud string, it will work just fine for stud strings. And for floats, and for, for so many types. I mean, that's the algorithm that figures the min value. Do I really have to write every one of those functions? No, I don't. What I can do is to abstract the notion of the affected type. Let's name it for the moment T, that's a convention. And it looks like this. There's no other change. But of course, C++ has this rule that before you use an identifier, you have to declare it. So let's do that. There's my declaration for T. This is a function template. I only have to write it once. The compiler will do the rest of the work for me, and we'll explore exactly how that happens. Okay? The standard says that a template declaration is written in terms of its template parameters, in this case, T. So T is an arbitrary type. I write class T, but you could just as easily have written type name T. They are equivalent in terms of the language. Function templates are often characterized as generic algorithms by which we mean that they are type agnostic. Whatever the type is, the algorithm is expected to work with it. And the type will be determined based on your use of the template. Okay? The compiler won't impose a type. It'll try and figure out what type is appropriate. And we'll see how that happens. Little piece of advice. If you're used to functions, we now have to distinguish between the classical function parameters and function arguments, because we now have template parameters and template arguments. Usually you can just say argument, and the context makes it clear which one you're talking about, but sometimes we need to be a little bit more explicit. So just a little bit of advice. All right, so what's the big picture? The point, of course, is that a compiler will treat a function template in the same manner that a builder treats a blueprint. It's a means for manufacturing something. A builder makes houses perhaps from a given blueprint. And he can make a lot of different houses from the same blueprint. In the same way that a compiler can make many different functions from a single function template. So it's a very good analogy, actually, to think of a function template as a blueprint for the manufacture of functions. Both function declarations and, separately, function definitions. They don't happen at the same time. Because we can make a declaration and then discover, say through overload resolution, that's not the one we're going to call. So the compiler does not waste the time to make the function that it's never going to call. Okay? It's when needed. When needed. Typically that means there's a call. But there are other reasons to manufacture a function. You might want to take its address, for example. Okay? But typically there's a corresponding call, or perhaps several. If you're new, please keep in mind that typically function templates are defined in headers, not in CC files. And the reason for that is actually very straightforward. The template has to be visible in its entirety at the point of use, right? Imagine a builder who is told, I have a blueprint for you, but I'm going to keep it in my drawer. Go build a house, right? The template has to be visible to the compiler at the point of use. Typically, the easiest way to do that is by putting the template definition in a header. So there are two principal steps that a compiler will undertake on behalf of a function template. The first one is known as synthesis. The compiler will synthesize a function declaration. Now, I'm actually exaggerating very slightly. It's not a full-blown declaration, it's actually just the signature that it needs. You don't need a full declaration to do, for example, overload resolution. Return type is not part of a function signature. Don't need the return type to do overload resolution. But it's easier to think of declaration versus definition because we're used to that. So I'm going to say declaration, but just keep in mind it's a slight exaggeration, all right? So we have function declaration synthesis, and then later, during compilation, we have function definition instantiation, okay? So those are the two principal steps. The nomenclature is that an instantiated function is known as a specialization. And it doesn't matter where the specialization comes from, okay? It doesn't matter how it's instantiated or when it's instantiated, it's referred to as a specialization. And a specialization is the same as a template declaration, except that every occurrence of the template parameter has been replaced by the appropriate template argument. That's the process of synthesis, and it's also part of the process of instantiation that we'll talk about a little bit later on, okay? So that's what specialization is all about. The point, of course, is that a specialization is specific to a type. It's no longer type agnostic, it's now type specific. And we can synthesize many, many function declarations from a single template. Now, the language does permit specializations produced by the programmer. These are known as explicit specializations. It's a form of customization. Normally, it's the compiler that synthesizes, for example, declarations and instantiates the definitions, but we can do this by hand if we wish. And the point of doing that is that you may have a general purpose algorithm, but for some specific type, there is perhaps a more efficient algorithm. So that is frequently cited as a reason to do an explicit specialization. Classical example is swapping. On certain architectures, swapping for integers can be done very efficiently with 3 XORs rather than the canonical move here, move here, move there, right? So that's a typical reason for doing explicit specializations. As we'll see later on, we should be very careful about doing that. So let's talk about the synthesis process. And let's look at this example. So here, of course, are 3 definitions. They look a little bit funny because I elided the bodies. Okay, so pretend there are bracing closed bodies as part of these declarations. Okay? Now, these are 3 different kinds of entities. The easiest one, the obvious one, is the third one. That's just an ordinary function. Very clear. The first one you recognize as a function template. But the second one is an explicit specialization. Now, how can you tell that's an explicit specialization? Well, look at what I've highlighted. Empty angle brackets. You see that? It's an explicit specialization. You need to look no further. Done. So I have a couple questions for you. Now, this is not an exam. It's not a quiz. Don't shout out answers. Don't raise your hands or anything like that. But take a few seconds and see if you can come up with an answer inside your head. Because right or wrong, I find that people remember things better having made a little bit of an effort first. The first question is, all right, I showed you some code up there. How many declarations do you see? And how many names are being introduced via those declarations? All right, take a few seconds. All right, everybody have an answer in your head? Yep, all right. Let's take a look. There are 3 declarations. I've even numbered them for you up above. That wasn't much of a challenge, was it? However, you may be surprised. There are 2 names being introduced because a specialization does not introduce a new name. It just recycles an existing name. We'll return to this point later. Okay? Yes, there are declarations that do not introduce names. I have more examples for you later on. Okay? So let's look at the same example again, no changes. But I have other questions for you. First, think about what happens when you call G. And here are some examples that you might want to think of, and pick a different type. Call it with a stud string. Call it with your type or my type. All right? Questions. How many declarations will be candidates for overload resolution for any one of these? And what are those candidates? Take a little bit of extra time and formulate a hypothesis. All right, everybody got an idea? All right, let's talk about it. By the way, I have to cut off the music because it's copyrighted. And okay, so from those same declarations, and I've taken away the numbers and given you a different kind of clue, the answer is at most 2 candidate declarations will be considered for overload resolution. Usually it's exactly 2, but there's a corner case where it's less. So what are those declarations? Well, one of them is really easy. It's the function. That goes into the mix. It's a candidate for overload resolution. Might not be chosen, but it's a candidate. Now, what's the other one? What's the second one? It looks like that. It is a synthesized candidate. The compiler has manufactured this declaration. Now, if you're like me, the first thought you have in your head is, what the dickens is that D doing there? Where does that come from? What is it? Well, it is a type that is often inferred by the compiler. Now, there is syntax such that you could specify it explicitly if you want, and we'll discuss that further a little bit later. But typically, it's inferred by the compiler. And after that happens, the primary template's declaration is copied, and then every instance of the template parameter he or T will be replaced by that inferred type, which I've here named D. Now, D could be int, could be double, could be float, could be stud string, could be your type, my type, etc. Whatever it is, that's the declaration that's going to be synthesized. And you can ensure the substitution of your choice by using that syntax in your call. Because inside the angle brackets, you can put your type. You may want to have a function that takes a double, but be able to call it with an argument of type int. If you want that, you're going to have to specify. The compiler can't figure out that's your intent. Otherwise, if you call it with an int, it'll figure, okay, you want a function whose argument type is int. Okay? But you have that level of control. Now, a lot of people are confused. They say, why is the template, and we refer to this as a primary template, as a distinction to a specialization, for example. So why is a primary template not a candidate? Why is it not in the list? Why is it not a candidate for overload resolution? Well, keep in mind that the ultimate goal is to pick a function that we can call. Produce it if we have to, but pick it. And the point, of course, is you can't call a template. Cannot do it. Why not? It's not callable. It's not a function. It's a template. That's why I'm so careful saying function template. Right? Can't call a template, it's not a function, it's not any other kind of callable entity either. I mean, there are lots of things in C++ that are callable. Function pointers are callable, right? Member functions are callable. Function objects are callable. Anything that has an operator parens is callable. Function templates aren't any of those things. Templates are never candidates for overload resolution. The compiler has to synthesize, or you have to specialize yourself to produce the declaration that is the candidate, never the template. For those of you who are visual thinkers, you may like this picture, just a different way of thinking about the same information. All right? A cookie cutter is akin to a function template. Oh, my apologies. Should I say biscuit cutter? Thank you. Sorry. All right? So the cookie cutter is akin to a function template. The cookie dough is akin to the template argument. Cookie is what you get. That's the function. And if you have a different dough, you get a different cookie. And the process of stamping out the cookie, that's instantiation. Got it? Good. So why is it that we can't call a function template? Well, it's the same reason that you can't eat a cookie cutter. Seriously. Would you try to eat a cookie cutter? Of course not. So why would you call a function template? Cookie cutter is not edible because it's not a cookie. A function template isn't callable. It's not a function. Okay? So a template can never be a candidate to be called. But the same way that you can use a cookie cutter plus dough to make cookies, you can use a function template plus appropriate arguments, one or more, to make functions. All right? And I find that analogy works very well for an awful lot of people. The point, of course, is that the compiler synthesizes this function declaration given the template declaration, function template declaration. But first, typically, it inspects the call, or whatever the reason is that this is called for. It looks at the call, and if appropriate, if necessary, it deduces the argument types based on what it sees as function arguments in the call. Then it substitutes those argument types in the place of the template parameters, and the result is that you get a synthesized candidate for overload resolution. Notice we have not yet made a function. We have only produced a function declaration. That's the synthesis step. Now, some people are still confused by saying, yeah, okay, I understand all of that, but we got a specialization there, an explicit specialization. Why is that not a candidate for overload resolution? And this is important. I find a lot of C++ programmers are utterly confused and find this counterintuitive. But it's really not. It has to work this way. It's a declaration, but some declarations don't introduce new names. And here are two examples that are unrelated. A static assert, if you look at the grammar, it's a declaration, believe it or not. Clearly, it doesn't introduce any names. Second example, consider a redeclaration. You say, int I, and later on you say extern int I. There's no new I, it's the same I. It's a redeclaration. Just because it's a declaration does not mean it has to introduce a name. And in fact, of more interest to our topic today, an explicit specialization does not introduce a name. And that's a quote directly from the standard. There's the citation in case you care to look it up. And therefore, specializations do not participate in overloading. And this is not new. Notice the date of this quote. This is 20 years ago almost. Right? This is not new. It's designed this way. This is the way it's supposed to work. Just because you write a specialization does not mean it participates in overload resolution. It's a separate issue, totally unrelated. All right, so moving away from synthesis, let's talk about instantiation. So far, we've got declarations, but ultimately, I'm going to need an actual function to be compiled. So where does that come from? Well, let's check an example. Suppose I have this primary template, I've gone through overload resolution, and we've made all of our candidates. And here are a couple of concrete examples. At some point, the compiler picks one, overload resolution, right? What then? There are two possibilities, two cases. If there is a pre-existing specialization that has the right characteristics. And this can come about in at least two ways. Maybe you've been down this path before. This is not the first like call. Or maybe there is an explicit specialization, right? So there are at least two reasons why you might be in this situation. If there is a pre-existing specialization and its arguments match the ones that were selected through overload resolution, then that's the specialization that's going to be compiled and ultimately called. Otherwise, the compiler has to manufacture the function. If it doesn't already exist, the compiler has to manufacture it. And how does it do that? Well, it's an analogous process to synthesis. But this time, we duplicate the entire definition, not just the declaration part of it, the whole definition, do substitution, including now the body, and now you have a function that's ready to be compiled and later called. Okay? So that's how we get functions out of templates. It's two steps. The first is manufacture the declaration, synthesis. The second, manufacture the function, the right function. All right? Now, it is possible to exercise some control over instantiation. This is not a common thing to do, but it is possible. You can force, I say demand, a template's instantiation for a particular argument. Even if you don't have a call, you can say, I need this instantiated here, now, in this compilation unit. The point, of course, is that this is how you can guarantee that the instantiation is part of a particular compilation unit, as opposed to leaving it up to the compiler. Okay? And this turns out to be useful, for example, if you're going to create a library and you want selected instantiations to be part of that library. Okay? And the way you do it, obviously there's always a primary template, and once you have that, if you wish, you can declare an explicit instantiation. Notice you have the template keyword and it's followed by no angle brackets. That's the syntax for explicit instantiation. Okay? You can omit that template argument if the compiler can figure it out a different way. But it's rare to find this in a header. I can't remember really ever finding it in a header. This might be something you want to do in a CC file, for example. Okay? On the other hand, the opposite is also possible. You can require that this not be instantiated in this compilation unit. You can prohibit instantiation. Now, you have to be careful, because if you prohibit it and there's a call, if you don't do anything else, this will not link, right? I'm calling a function. I've denied the compiler the ability to manufacture it for me. Can't, you know, it's like a freshman mistake. Call a function and don't provide the function, right? So you have some extra responsibilities. You have to ensure that there is an instantiation somewhere, and that's how the compiler can get away with not instantiating it here. You're taking control. With power comes responsibility, right? So you have to be a little bit careful, but how do you do it? It's almost the same as saying, do it here. Well, don't do it here. You just put the keyword extern in front. The specialization will be elsewhere. Okay? Again, you can omit the template argument under the same conditions. This can be sometimes useful in a header, because headers get included several times. You may want, you know, don't in general instantiate this thing. I'll take care of it somewhere else. Still not a common thing to want to do, but you do have that level of control. All right? Just wanted you to know that. It is not particularly well known, I've discovered, that occasionally the compiler can actually manufacture the whole template behind the scenes. This is sort of the canonical example. First, a quick reminder of something that seems unrelated, but bear with me for just a few seconds. A lambda expression, when evaluated, as you know, produces what's called a closure, which is a special kind of function object that the compiler makes for you as part of evaluating a lambda expression. Okay? Keep in mind, a lot of people talk about calling a lambda. You can't. You can't call a lambda. Evaluating a lambda gives you a closure. You can call the closure, because that's a function object that's callable. Okay? And the interesting part of this, of such a lambda, and let's look at this particular example, very simple lambda. This object named lambda1 has a type whose name we mortal programmers cannot utter. The best you can say is decal type of lambda1, right? But it looks approximately like that. And if you haven't encountered this before, why do we need closures? Well, imagine if there were captures. Where would you put the capture? Well, they go into the function object. Okay? All right, so what does it have to do with function templates? Well, this is C++ 11. Ever since C++ 14, we've had generic lambdas. See that auto? That's a generic lambda. What do you think is the type of lambda 2? It looks like that. The call operator is a function template. Okay? The compiler has actually manufactured a function template in response to your having written a generic lambda. So even if you never write a function template, but you choose to use a generic lambda, you're actually using function templates behind the scenes. Okay? I thought you might find that interesting. All right, so some special topics now that all relate to function templates. Let's talk about parameters and arguments. So an important step in the manufacture of declarations and definitions is obtaining the template arguments. How does the compiler do that? It's not easy. The first possibility is that maybe the programmer wrote it down explicitly. So here's a possible call to some function template G1. Says float. Okay, there's my template argument. I got no work to do, I'll just copy it. Oh, and by the way, you can write that, and it's a different instantiation. It has the same type, same function type, but it's a different instantiation. All right. Different specialization, I should say. All right. So that's case one. Now, most of the time, programmers don't write this down explicitly. So the compiler has more work to do. So possibility two is to try and infer it. This is a process known as type inference, right? So the compiler tries to infer it by inspecting the function argument. And notice I say, if possible. Now, we'll talk about how that happens in another page or two, but I want to show you some examples of why it's not always possible for the compiler to do this. And I've not found these examples collected anywhere. So here are three little examples. Example number one, just look at the code. This is like saying, hey, I'm going to tell you my shoe size, you figure out my ethnicity. What? All right. Hey, I'm a type. My size is 96 bytes. What's my type? Sounds like a game show, doesn't it? What's my type? 96 bytes, I don't know. Some number of ints, some number of doubles, some combination, your type, I don't know what it is. There's no way to figure it out. I can't do it, the compiler can't do it. All right? So that's one example. Second example, somebody's brought me a present, but somebody, my kid, to be helpful, has unwrapped it for me and given it to me unwrapped. Okay, what did the wrapping look like? Or was there any wrapping? I can't tell. This is what it looks like after the wrapping paper has been removed. How can I recreate what it looked like originally? All right, we've removed the reference. Okay, it says int. What was it originally? Was it int originally? Was it int ref? Was it int ref? I don't know. I can't do it. Can't figure it out. Doesn't work. Can't do type inference. Final example. A function template that has two function parameters of the same type. But look at the call. I'm calling with arguments of two different types. All right, which one, guys? There's no basis for a decision. Compiler can't do it. So here are some reasons why the compiler might fail at type inference. But there is a possible fallback. Step 3, if you get that far, step 3 says, go see if there's a default template argument. And if there is, use that one. Okay? So collectively, these 3 steps are known as type deduction, of which type inference is the middle step. But most people just say type deduction and think it's only the middle step. But the standard is just a little bit more precise than that. All right? So let's look at type inference just by itself. Okay? As we've seen, type inference can fail. The success and the result depends on several different things. It's going to look at both the type of the function parameter and contrast it, compare it to the type of the function argument. Now, that sounds at face value wrong, because our goal is to come up with the template argument. But the basis for the inference is the relationship of the function argument to the function parameter. That's what the compiler will look at and do its inference based on that, and whatever it comes up with becomes the template argument. Okay? It's important that you understand conversions do not enter into type inference. Imagine trying to figure out a type and suddenly realize it can convert itself to anything else. You know, you're at int. Oh, you can turn into a double too? Oh, you can turn into a string? You can forget about conversions. It's not a factor here. Just not at all. So I'm going to show you a table on the next page. Here's the build-up to the table. Assume I have a function template G, and the type of the function parameter can be any one of 6 types, which I've enumerated for you. It could be an unvarnished T, it could be a T-ref, T-constref. I refuse to consider volatile at the moment. Okay? But this is enough to get us started. Okay? We're going to look at each of those cases. What will the compiler do for each of those 6 cases? And in particular, we're going to look at 6 calls. So I'm going to show you a 7x6 matrix in just 1 second. Okay? So notice my coding. All right, K is an int, KL is an L value reference type, KR is an R value reference type, etc. Okay? C means this const is part of the type. All right? So that's the key to the matrix on the next page. Everybody got it? All right, good. So if the function argument is a simple T, that's call by value. All right? So if I call with argument of 42, it's an int. It's just a copy of the int. In fact, in every one of these cases, T will deduce as int. It's called by value. Very straightforward. T-ref. Well, the top line is interesting, but that's just ordinary rules of binding. You can't bind an R value to a non-const L value reference. ordinary rules. So it would deduce int, but that can't happen. The rest of it, int, and then int const all the way down. Does that make sense to everyone? Right? You have to throw in the const because it's not already there in the parameter type. Now, when const is there in the parameter type, we don't have to deduce it. What is t? See, the parameter type is t const ref. So t is just int. The const is supplied by the parameter type. Okay? T const ref. This is almost useless. And frankly, I've never found an application that calls for this. I have, I think, once seen code that uses t const ref. But it's effectively useless. There's only one way you can possibly call it. You have to provide an R value. Right? And the rest just don't bind. Now, perhaps the most interesting one is this case, tref, which has a special meaning, and it's not R value reference to t. Sorry. Now, that's what it would mean if we were talking about a function. This is a function template. It has a special meaning. This is what is known as a forwarding reference. Okay? And the point of a forwarding reference is that you end up figuring out exactly what the right type is and matches the type of the parameter. So I have not found a matrix like this anywhere online. It might be there, but I just haven't found it. So I hope you find this useful. 2 footnotes. Type inference is not limited to this context. It arises in other places in C++ just as well. For example, if you declare a variable as auto, and there's a reason why the same rules work there. The reason is we designed it that way. No new rules when you use auto. The way the compiler figures out the exact type of that variable is exactly the same way that the compiler would figure out the type of the template argument. No new rules. And the other thing to recall is that in C++, parameter passage is initialization. When you call a function, you are initializing the variables that are the parameters. Okay, so it's not surprising that these have identical treatments. You can initialize a variable, you can initialize a parameter, it's really all the same thing. So there should be no surprises here. Okay? All right, let's move on. Partial ordering, a very misunderstood topic. Sorry, is that time left? No, I don't think so. We have 90 minutes.
Oh, we got 90 minutes. Oh, sorry.
50% more time, 70% more material, people. And by the way, before I forget about it, ooh and ah, my wife made this tie for me. Please help me thank her. I appreciate it. I'll make sure she sees this part of the video. Oh, that's quite all right. I was a little bit surprised. That's all. All right. Partial ordering. I've discovered very few C++ programmers have a good handle on this. Here's a situation that can arise. It isn't particularly common, but it does happen. We can synthesize function candidates from more than one template. Yes, function templates can overload each other. I can have 2 function templates named Go. And each one might contribute a candidate. Oops, now what? Aha! Partial ordering to the rescue. Okay? Partial ordering is the algorithm that the compiler uses to decide which candidate is preferred. Some people think of it as a separate step. Some people think of it as rolled into overload resolution, it doesn't really matter. It happens during or associated with overload resolution. And the ordering is partial because there are cases when the compiler simply can't decide. Okay? They're not always going to be ordered. The point, of course, is that the compiler during overload resolution is looking for the most specialized of the viable candidates. Now, viable is one of these words of power. That just means we potentially can actually call this. Functions can be not viable for lots of reasons. The most obvious one is it's got the wrong number of arguments. I'm supplying, parameters. I'm supplying one argument, but this function takes 2 parameters. Well, it can't possibly be called. This is not viable. Okay? So of those candidates that are viable, we have to pick the the most specialized one. So look at this example. Say we have one function template that has a function parameter t, and there's a second function template by the same name that has a function parameter of type t star. Okay? Now suppose I make a call and the argument in the call has a pointer type. Both of those are viable. In the one case, t will be a pointer type. In the other case, t will be the pointee type because the star is already part of the parameter. Okay? So here's a test now. Let's overload the name H. And this is valid code. I'll give you a few seconds to look at the example. I've labeled them A, B, C for reference. And now think about calling H. Here's the call, H of P. See what you can figure out. I'll give you a few seconds. I'll give you a little extra time. This is not quite as easy. All right, everybody got an answer in your head? Okay. Well, there's the answer. It's going to call some implicit specialization of template C. In particular, it's not going to call B. You may find that surprising. I know a lot of programmers do. Think about what are the candidates. And remember, we're looking for the best possible match. So here are your 2 candidates. One is contributed from A, and it looks like that. And the other one is contributed from template C. Remember, specializations are not candidates for overload resolution, so B is not a candidate. Okay? And you look at those and you say, which one is more specialized? And the answer is the one generated from C. Well, wait. That specialization B, that's exactly what I'm looking for, isn't it? Sorry, not a candidate. Well, how do we know that B is a specialization of A and not a specialization of C? And trust me, this is a question that you could have answered when you took your first course in programming. It's just ordinary name lookup. At the point that you see line B, you haven't yet seen line C. It's a specialization of what? The only candidate is A. I haven't seen C yet. I don't look for declarations in the future. So B has to be a specialization of A. Can't possibly be a specialization of C. But it's the candidate from C that wins. And so we actually have to have the compiler instantiate a function from C. Okay? Where B is declared, only A is in scope. C is not in scope. So B cannot possibly be a specialization of C. There's no look ahead. Okay? Let me permute some things and ask the same question. Same declarations, but I've swapped two lines. Right? This is the what if that a lot of you, I'm sure, were thinking of. Yeah, I've done this before. Okay, so does the answer change? Go. Everybody ready for the answer? Now we're going to call B, because it's a specialization of C. The candidates are exactly the same as before. Okay? What changed? Well, this is interesting. We already did a first round of overload resolution. I think it is not particularly well known, but function calls are not the only reason for a compiler to do overload resolution. Hey, I'm a specialization. To whom do I belong, please? Oh, got to figure that out. Ah, overload resolution. List of candidates. Let's see which one is best. Okay? So what changed? Well, both A and C are now in scope at the point that you see B. So we do partial ordering, which is part of overload resolution. It's going to pick C as the primary template that matches B because it's more specialized. Even before we see a call, compiler has to figure out, this is a specialization of what? Okay? One more. Restore the original order and append one more line. Okay? Yeah, B and D are pretty similar, aren't they? This is a valid code, people. It's valid code, no tricks. Okay, you can try it. With a modern compiler, please. All right? All right, go. Everybody got an answer or a guess? This time it's going to call D. D as in dog. Because D is now a specialization of C in the same way that B is a specialization of A. All right? B has to be a specialization of A. There's no other choice. D does have a choice, but for the reasons we explored previously, right? So here I've rewritten B and D with the substitution made explicit. Okay? Does that help? Good. I'm glad. Okay. Now let's look at explicit specialization. As we said earlier, typically this is done to improve algorithmic performance in some specific case by putting down some instructions that are specific to that case, right? And I mentioned this already, the generic swap algorithm has 3 copy or move operations, but sometimes you can swap unsigned ints by doing XORs, and in some architectures that's a lot faster. So that might be a good reason for a specialization, for an explicit specialization. There are other names for this from lots of different contexts. In C++, they all pretty much boil down to the same thing. Tuning an algorithm, customizing an algorithm, tailoring it, just specialize it. Please, please, please The language does not do this for you. But if you're going to specialize, please make sure you get the same result that you would have gotten from the generic case. I guarantee bad things will happen if you don't. And I've seen it. Okay? So be very, very careful. The compiler will not help you if you violate this strong advice. Okay? So be very careful. This is new for C++ 17. There used to be some mildly odd restrictions on where you are allowed to physically now to place the explicit specialization. All of those restrictions have been removed as of C++ 17, and now you can put the explicit specialization anywhere in the same scope as you have placed the primary template. If you're not doing C++ 17, please look up what the rules are. They are not quite this liberal. Okay, there were good reasons for them at the time. Those reasons are pretty much gone now. So this is a change as of C++ 17. We have not talked very much about function templates as members, so here are just a couple of examples of how you might write an explicit specialization of a function template that is a member, in this case of a class. And if you choose, you can do this outside the class, or you can do it inside the class if you want it implicitly inline, for example. But notice, it's an explicit specialization because of the empty angle brackets, same as before. But now we say A::G, here's the explicit argument, and go on with the rest of it. Or, what if you have a function template that is a member of a class template? The template parameters are independent. So you actually have to say template twice. Template class T, that's the template parameter for the class template. And now you say template angle brackets, there's the specialization of the member template. Okay? So this is what it would look like. Now, don't get excited about the syntax, because you really shouldn't do this. Let's talk about that briefly. Customizing a function template by doing explicit specialization is considered by many programmers, whom I respect a lot, to be a bad idea in general. Now, if you need to do it, you need to do it. But if you don't, I'll give you some suggestions on what you can do instead. The principal argument is that the presence of explicit specializations does not, as we've already discussed, interact with overload resolution in the way that naively most C++ programmers would initially believe. Right? Naively, a lot of C++ programmers, not you folks any longer certainly, believe that a specialization is part of overload resolution. And as we all know now, it's not. Okay? Quote, overload resolution does not take into account explicit specializations of function templates. Only after overload resolution has chosen a winner will any explicit specializations be considered. And this is not a new rule. It has always, always, always worked like this. But an awful lot of C++ programmers simply don't know that. So the advice, of course, is to avoid explicit specialization as a customization technique. There are other choices. If you do need to customize, your first fallback should be just an ordinary function that overloads the template. Because there's a language rule that says if you have a function versus a function template specialization, the function always wins if it's otherwise a tie. Right? So it's a perfectly viable approach for customization, if that's what you need to do. If you must specialize, keep in mind that The advice about explicit specializations does not apply to class templates. Class templates don't overload, right? So there's no reason to avoid explicit specialization of class templates. They don't work the same way. There's no overloading involved. So do the specialization, do all the work using class templates that are function objects when instantiated, and then write your function template simply to forward to that class template. And that just works. Customize the operator parens in the class template, and that's going to work just fine for you. And it would look approximately like that. Okay? So there's some choices for you. We have one more choice as of C++ 17. Const_expr if as an alternative method of specialization in a function template. Now, if you haven't used const_expr if, the one important thing to keep in mind is that one of the branches will be turned into what's called a discarded statement. But that does not mean that you can write anything even though it's going to be discarded. It has to be valid C++. Okay? It can't be garbage. It has to be at least parsable. Okay? But once you've done that, let me show you an example. Suppose I want to calculate x to the nth power where n is known at compile time. Not runtime, but compile time, right? Now, when we teach kids about exponentiation, we always say it's the short form of repeated multiplication, right? You want x to the 8th, you line up 8 x's and you multiply them. But we all know that there's a faster algorithm to do that. Take x, square it, square that. You're done. 3 multiplications instead of 7. Well, that's logarithmic behavior versus linear behavior, right? So we want the faster algorithm. Sounds like a special case. Look at this. A function named power that has 2 template parameters. Oh, wait, what's that first one? That's not a type. That's a number. Yes. Templates don't have to have parameters that are types. They can have parameters that are values. Certain values. Don't do floating point there. That's the notable thing to avoid. All right? But n would have to be known at compile time, right? Because the compiler has to do the synthesis and instantiation. But look at the cases. Const_expr if it turns out that n is 0, the answer is 1, and discard the rest of it. I've customized it for n equals 0. Else, if const_expr it's even. Well, square it and then do it again with n divided by 2. Otherwise, n is odd. Do an extra multiply by x, and then subtract 1. Now, you can code this differently, of course. You can code it slightly more efficiently and so forth. But I do it this way because I think it makes it very clear what's going on. But there's 3 cases there. And before C++ 17, you pretty much had to write a template and 2 specializations. Okay? So this is a viable alternative. And from my perspective, this is very clean because everything's in one place. I can read this and understand very quickly what's going on. I hope you can too. Okay? It does not fit all situations. It's not a panacea. But it fits a lot of situations. So a new tool in our toolbox. Oh yeah. Robert Heinlein, bless him. Specialization is for insects. And for compilers. Not so much for us programmers of function templates. Okay. All right, friendship. Friendship is the strongest possible relation that you can have between types and functions. Now, recall how friendship really works. I've discovered that not all programmers understand this very well. If you write a friend declaration, you're writing the declaration in the middle of a class, but what you're declaring is not a member of the class. So where is that thing that you're declaring? It's not in the scope of the class. Can't possibly be. It's not a member. Where does it go? It goes into the nearest enclosing namespace. But it's not visible. Okay? Yes, this is a little bit out of the ordinary. But that's what friendship really means. If you want it to be visible, you need a declaration in that namespace. The friendship declaration by itself does not make it visible. So if all you have is a friend declaration, ordinary name lookup will not find it. Some people refer to that as a hidden friend. Class A declares a friend function go. You try to call it, will not compile. It's not visible. If you declare it in the right namespace, now you can make the call, it is visible, and it'll work. But until you have that declaration, it's not visible. Now, the situation's a little bit different when there are function arguments, because when there are arguments, you have ADL. And ADL will find it, because it's an associated namespace. Okay? But normally, you should do it like this. Now, you can put the declaration up front, right? Declare it and then make it a friend, which is what I recommend, and then you never have any issues. Okay? So that's just by review. Now, how does this tie into function templates? Well, because you can grant friendship either to some specific specialization, because remember, a specialization is just a function. So I can say, you're my friend. The rest of you, not so much. Or I can grant friendship to all specializations. Okay? And the same rules hold. No new rules just because it's a function template. Okay? So assume I have a function template go. I grant friendship to go of int. So only go of int is my friend. Or I can say, hey, all you guys named Go, you're all my friends. And I can even tune it. If I'm a function template, I can say, hey, you function Go who has the same template argument that I do, you and only you are my friend. But if there's a second instantiation of the class template, it'll have a different instantiation of the function template as a friend. Okay? So just some things to think about. We have choices. We have some choices here. Okay? All right, let's talk a little bit about the future. I feel like a movie trailer here. Coming soon to a compiler near you. So I want to talk about two things involving function templates that are happening, that are likely happening for C++ 20. One in the core language and one in the library. Let's look at the library first. Historically, C++ has allowed programmers to provide explicit specializations of any of the templates in the standard namespace. Those of us who implement the standard library hate that. Because some of your colleagues write really, really weird code. Seriously, weird code. And we have to do really oddball stuff in the standard library to cope with that. And that's both time-consuming and painful and leads to really weird code in some places. If you ever look at a standard library implementation of some of the classical algorithms, for example, hardly anybody uses post-increment. We contort the code, even if it were the most natural thing to write. Why? Because some people write iterators where post-increment really does an internal copy, and we don't want that copy that's ultimately just going to be discarded. So we rewrite and contort the code to use only pre-increment. Here's another one you may never have thought of. You have colleagues who overload the comma operator, God help us. And the address of operator. Well, number one, please don't do that. All right? But in the standard library, we have to cope with that. And you will find, if in the standard library, if you have a loop that has to do an increment of two different variables, where you would naturally write, you know, plus plus I comma plus plus j, we'll never write it like that. There's going to be a cast to void. So it'll be, you know, plus plus I cast to void, comma, plus plus j. Because that is never an overloaded operator. It's our, you know, you have colleagues who write really weird code, people. Clearly nobody in the room does that. Nobody watching this on video does that, of course. But we have to go through hoops to be sure that the standard library code works. Well, we want to carve out a little more leeway for ourselves. The current rule is that, subject to these two constraints, you are allowed to specialize anything in the standard library. We would really like you not to do that. I mean, these constraints are perfectly reasonable, but we don't want you even to do that. Yeah, this makes life difficult, no kidding. So the permission is being withdrawn. You don't get to specialize anything in the standard library except things we specifically say you get to specialize. Okay, and there are very few of those. Some algorithms are being respecified as what are going to be known as either customization points or customization point objects. And you will be allowed to specialize those. The canonical example is stud swap. Of course, you have to be allowed to specialize stud swap. Okay? But not by explicit specialization. You can write your own function by the same name in your own namespace. Stay the hell out of stud, and we'll find your function. We know how to do this. There's a paper by Eric Niebler, which is about 3 or 4 years old now. I have a link to it at the end of the talk. We know how to do this, and we can do it even better now in C++ 17, because now we have inline variables. That makes a difference. Okay? So we know how to do this. You could do it too. It's not particularly difficult. So in the future, if you have to customize something in the standard library, do it in your own namespace. And if it's a customization point, we'll find your function. Which means you can make a call in generic code. You can call it either qualified or unqualified. We'll find it. This works. The bonus is, if you're writing generic code, again, today you have to do what a lot of us call the two-step dance. Bring the standard thing into scope and then call swap unqualified, for example. Because that way we'll pick up all the overloads named swap, including the one in the standard library. Won't have to do that in the future. You can, for example, just do that. It'll work. We'll find your overload in your namespace, assuming it's in scope. All right? But please, stay out of standard namespace. Do us all a favor. You'll like the result. You really will. We can do better things for you. if you stay out of our way. So that's one. The other item I want to talk about is in the core language. Been a lot of work involving concepts. This is an outgrowth of some of that work. It looks like we're going to have another way, a simpler or at least shorter way of writing function templates starting in C++20. And the idea is that it's based on generic lambdas, which already use an auto-based syntax. So you will recognize this in C++17. This is return type deduction use of auto. That's been around since C++11. It looks like we're going to get this. It means the same thing. No keyword template. Now, they're not quite the same, because if you write it the new way, you don't have a name for the deduced type. But surprisingly often, you don't need to refer to it. And sometimes you can get by with decal type, or you can get by with auto. You don't always need the name for the type. And if you don't, this might be a shorter way of writing a function template in the future. It's also intended to work with constrained declarations. As many or most of you already know, constraints are new in C++20. They come in with concepts, right? We have constrained declarations, and you constrain with a concept typically. And the informal rule, at least the intent is, you can write a constraint followed by the keyword auto wherever you can write the keyword auto. Okay? So here's sort of the canonical syntax ever since the concept's technical specification, and that will be allowed, it seems, in C++20. So you can do it this way. Or this is the notation that Alexander Stepanov has been wanting for 20 or 30 years, and we're going to allow that. Of course, in both of these examples, sortable is the name of some concept, right? So we're going to allow that. We still have a name here for the ultimate type, right? Or simpler syntax, just write it like that. And it all means the same thing, modulo the availability of the name. Okay? So it looks like that's coming down the pipeline. All right, so what haven't we talked about? As we all know, there's always more to learn about C++, one of the things that attracts a lot of us. Well, of course, we have other kinds of templates. We've had class templates for a long time. We got alias templates in C++11. We got variable templates in C++14. I apologize for making you wait that long. I proposed them in 2004, but didn't push them hard enough at the time, so it took a decade. I'm sorry about that. Templates with multiple template parameters. Most of our examples have been single template parameters. There's some interesting things that happen when you have more than one template parameter. Templates that involve parameter packs, templates that involve more about non-type template parameters, like that unsigned I showed you earlier. That's a non-type template parameter. Template parameters that are themselves templates. Say what? Yeah, they're called template parameters. They are the metaprogramming equivalent of function callbacks. Think of them as metafunction callbacks. They work. They're beautiful. They confuse the hell out of your colleagues, but they work. A new feature in C++17 that I pushed very heavily, yeah, my name is on the paper, but sort of by courtesy, CTAD, Class Template Argument Deduction. We used to, when you wanted to declare a vector of int, historically, you had to write vector of int, variable name, initializer maybe. You don't have to say int anymore if there's an initializer, because the compiler can now deduce that type, because the constructor, after all, is just a function. All right? So we know how to do that. There's template metaprogramming. Some of you may have seen my cppcon video from 2014. Thank you, by the way. I'm very flattered. It's had like 50,000 views and still gets something like 1,000 a month. It's unbelievable. Thank you, thank you. Constrained templates, there's a lot to learn there. This is new for C++20. We've had this ever since the concept's technical specification, and it's pretty solid for C++20. There is a book. If you really, really, really want to master templates, read this book by the masters of templates. David van de Voorde et al. Excellent book. Be sure you get the second edition. First edition is still valid, but you really want the second edition these days. Highly recommended. Here are some online resources. I've quoted some of these. Here's where the quotes are from. Here are some papers that were written. This is the one I mentioned by Eric Niebler from a few years ago. This is a very recent paper, Differences Between Functions and Function Templates, a very interesting paper. And with that, I thank you all very much.